So our next chapter is application of partial differentiation, and our first topic is this Taylor's theorem for function of two or more variables. So let's consider a function f of x plus h comma y plus k as a function of single variable x. So that means this term is constant. Now by Taylor's theorem, if we expand this function, we get as follows, and so on. Now let's consider this function f of x comma y plus k as function of y variable only. So this one becomes a constant, and we use same Taylor's theorem and expand it. Then we get f of x comma y plus k dou by dou y of f of x comma y plus k square by dou factorial dou square by dou y square of f of x comma y, and so on. Now substitute this equation in our first equation. Then f of x plus h comma y plus k would be equals to, we would get like so. Now these terms are all over the place, so let's rewrite this equation in an orderly fashion. Then we would get f of x comma y plus h dou f by dou x plus k dou f by dou y. Take 1 by 2 factorial common. Then in that we would get these terms. And so on. Now if we take x equals to a and y equals to b and substituting over here, then we would get f of a plus h comma b plus k equals to f of a comma b plus, now we get like so. I just changed some of the notations here. I hope you guys don't get confused. So f of x and dou f by dou x, they're both the same. Putting a plus h equals to x and b plus k equals to y. Now this x and y and this are completely different. We're just noting these two variables as x and y. So we have a plus h equals to x and b plus k equals to y. That would also mean h equals to x minus a and k equals to y minus b. Substituting these in the above equation, we would get f of x comma y equals to f of a comma b, and h is x minus a. We would get this equation. Now this is called as Taylor's expansion of f of x comma y in the powers x minus a and y minus b. So basically this is used to expand this function f of x comma y in the neighborhood of a comma b. Now you don't need to do the whole thing, you just need to try and remember how the expansion looks like to apply it in our problems. So to get Maclaurin's expression from this, substitute 0 in the place of a and b. So a equals to 0 and b equals to 0. Then we get f of x comma y equals to, this is Maclaurin's expression of f of x comma y. So let's take a problem. They gave us f of x equals to x to the power y of powers x minus 1 and y minus 1, and they asked us to expand. So we're going to use Taylor's expansion. So like we saw before, Taylor's expansion of f of x comma y in powers x minus a and y minus b would be f of x comma y equals to, so that's how our expansion looks like, and it's pretty easy to remember. If you keep the derivatives aside, it kind of looks like a plus b whole square formula, right? And this one kind of looks like a plus b whole cube formula, so it's kind of easy to remember. Now comparing this to our given problem, x minus a and x minus 1, y minus b and y minus 1, so that would mean a equals to 1 and b equals to 1. They usually specify up to how many degrees we're supposed to do it in another question, but if they don't, it's better to do till the third degree. So we're expanding up to the third degree here. So let's just find all the derivatives first and then substitute the value and then substitute it in the formula. So we're gonna find out f of x, f of y, f of xx, f of yy, f of y. So f of x, our function, we are partially differentiating it with respect to x. So that would be y into x power y minus 1. Now f of y partially differentiated with respect to y. It's in the form a power y because x is going to be constant. Then our formula would be a power y into ln a. So ln x into x power y, and f of xx, partially derivate this with respect to x, we would get y into y minus 1 x power y minus 2. So similarly we find out the derivative for the remaining 6. This is what we get. So now for every derivative, in the place of x and y, substitute 1 comma 1 because that is a comma b. Then we would get, so we're going to substitute 1 comma 1 here, then we'd get 1. If we substitute it here, ln of 0 is 0, so the whole term becomes 0. And when we substitute 1 over here, this term becomes 0, so the whole thing becomes 0. So wherever we have y minus 1, it is 0. That is 0. This one has y minus 1, so it would be 0. ln x, so that would be 0 as well. F of x comma y, this term is 1 and this term is 0. And when you substitute 1 over here, we get minus 1. So this would be minus 1. And f of x y, this term is 0, and when you substitute 1, we get minus 2. Now take these values and substitute in our Taylor expansion formula. So that would give us f of x comma y, so x to the power y equals to f of a comma b. So x power y, you substitute 1 comma 1, we would get 1 plus x minus 1, f of a comma b is 1, so it's that, plus y comma b, f of y comma b is 0, so that term gets cancelled, so this is still here. Then 1 by 2 factorial, f of xx is 0, f of yy is 0, and f of xy is 1. So f of xx is 0, f of yy is 0, and f of xy is 1. So we only have this term. Then we'd get 2x minus 1, y minus 1, that's 1. 2 factorial is 2, so 2 gets cancelled, plus 1 by 3 factorial into f of xx is 0, f of y is 0, so we have f of xxy and f of xyy. You can take 3 common, so x minus 1 square, y minus 1, f of xxy is minus 1, so it's minus 3, plus minus 2 into, we already have a 3 here, x minus 1, y minus 1 square. So 3 factorial is 3 into 2, we can cancel 3. So this is the Taylor expansion for the function x to the power y in the powers of x minus 1 and y minus 1.